Hello, welcome back to our course on advanced quantum mechanics. Remember, we found out that to solve a quantum mechanical problem is to solve 3 challenges at once. So, to solve a quantum mechanical problem, is to solve these. First of all, you need to solve the hermeticity condition. Hermeticity conditions, namely that the x hat of t dagger is equal to x hat of t, and the p hat of t dagger is p hat of t. And if we have many of those, we have for each hermeticity condition, then we also have to solve the canonical commutation relations, and they would be x hat of t, p hat of t equal to I h bar delta ij, like this, and then similarly that the x's commute. And finally, we also have to solve the equations of motion, right? And the equations of motion are given by the Heisenberg equations of motion. They are x hat dot indicating time derivative, x hat dot I of t equal to 1 over I h bar commutator x hat I of t with the Hamiltonian. And similarly for the momentum, it's 1 over I h bar commutator of p hat of t with h hat. And that dot should not be there. Okay. We managed to solve all of these conditions for the simplest possible quantum mechanical problem, namely for the case of the free particle in one dimension. The case of the free particle. There, the Hamiltonian was p hat squared over 2m, and the equations of motion were, of course, that x hat dot is equal to 1 over m p hat, and that p hat dot was equal to 0. Right? Momentum is conserved for a free particle. So our challenge was to solve, yeah, this is going to be difficult, creating a new page, okay. All right, so the challenge was to solve the hermeticity condition, the canonical commutation relations for these equations of motion. And what we found is that we can solve these equations by making use of a particular very useful matrix that helps us fulfill the requirement of a particular kind of non-commutativity, namely given by the canonical commutation relations. And ultimately, what we saw there was that a strategy works out, which is a strategy that is used in quantum physics all over the place. It's not universally applicable everywhere, but you can solve very important problems with that For example, even the calculation of Hawking radiation of a black hole is based on this particular trick that we already applied in the previous lecture to solve just a free particle in one dimension. And what is that trick? The trick to solving these three problems that we always have to solve simultaneously in quantum theory, the trick that is very often useful is that we separate the problem of solving the canonical commutation relations from the problem of solving the equations of motion. In other words, we are trying to solve the problem by writing the solution as a product of two expressions. One expression is supposed to take care of the non-commutativity, but it has no time dependence. And the other factor has the time dependence that is needed to fulfill the equations of motion, but it has no non-commutativity. Right? So we are separating the problem of solving the canonical commutation relations from the problem of solving the equations of motion by writing our ansatz for a solution as a product of two factors, one of which takes care of the non-commutativity and the other one takes care of the time dependence. Let's see how that panned out in the case of the free particle. So what we did there was we defined a matrix, namely we defined A to be this matrix, an infinite by infinite matrix, which had these entries, square root of 1, square root of 2, square root of 3, etc. And all the rest is 0. Very simple matrix, but it's an infinite by infinite matrix. And then we used it to create exactly such an ansatz which, by the way, are you all familiar with what an ansatz means? An ansatz means an attempt at guessing the structure of a solution. That's an ansatz. Actually, the word ansatz is a German word, and what it means is it describes when a cat is about to pounce on a mouse, and a cat gets into position, right? It gets into position to jump. And that's an ansatz. And I guess we get into the position to jump and solve the problem here. Okay. All right, so we define the matrix A. And then, just a moment, I need to create here some more space. Okay. Oh, this is tedious. Okay, there we go. Right. So then we made the ansatz that x hat of t naught is equal to some number times a dagger plus a. So that's an infinite by infinite matrix now. And we made the ansatz that p hat of t naught is equal to IH bar over, so this is a definition, right? We just try this out. I over IH bar to L, and then a dagger minus a. With this ansatz, we found that we have already solved the canonical commutation relations and hermiticity. First of all, hermiticity is usually easy to solve. When you want to solve a quantum mechanical problem, the hermiticity condition is usually the easiest. And why is that? Well, let me show you. Hermiticity is okay. How do we know that? Well, because you see, x hat dagger is equal to x hat, because let's look at the structure of this thing here, of this expression. All we need to do to ensure that this expression is Hermitian is that we choose L real, right? If L is real, then the dagger of this expression here is going to be L times A plus A dagger. So we have hermiticity. And let's check now on the right-hand side here for the expression for the p hat. If we take the dagger of p hat, then A dagger and A trade places, so we pick up a minus sign, but we also take the dagger of I. But remember that the dagger of a number is the complex conjugation of that number. So it's minus I, and therefore, again, we obtain that p hat is p hat dagger. So hermiticity is easy. And why did I say that hermiticity is always easy to create, always easy to fulfill when you try to solve a quantum mechanical problem? Well, it's because whatever your ansatz may be, whatever your guess for a solution is, you can simply add to it its Hermitian conjugate, and then you get something that's Hermitian, right? So for example, if we had guessed that x hat of T naught ought to be L a dagger, well, then we only need to amend our guess by adding to it L a, because, L a, because that's the Hermitian conjugate. So the whole thing is Hermitian now. So generally, the strategy is going to be that whenever we make an ansatz, we just add the Hermitian conjugate to it, and that will guarantee that we have hermiticity. And this also will mean that later on, when we solve more complicated problems, when we pursue this super powerful strategy of writing the solution as a product of two factors, one of which is commutative but has the right time dependence, and the other one has no time dependence but is non-commutative of the right kind, then we will write down this product, check if it's Hermitian. If it's not, we add its Hermitian conjugate, and then we have the hermiticity condition fulfilled for free. Okay, so the hermiticity is okay. What about the canonical commutation relations? Well, you have to plug it in, and I leave it to you as an exercise to show that with these prefactors, an L here and the IH bar over 2L, the commutation relations actually come out fine. So CCR, this is C homework. Okay, now how about the equations of motion? Well, easy. Remember, one equation of motion was that the time derivative of the momentum is 0. So therefore, we already know that p hat of t is equal to p hat of t naught. Easy. And then we also had that x hat dot of t is equal to 1 over m p hat of t, but we can already write t naught because we know that it's not time dependent. And from that, we can already tell that x hat of t has to be x hat of t naught in order to fulfill the initial condition, and then t minus t naught times 1 over m p hat of t naught. Let's just check. If we do the time derivative on the right-hand side, the first term goes away because it has no t dependence, it's a constant. And in the second term here, we have that we differentiate with respect to t. The only t dependence is right here, and then we get its p hat over m. So we have that the equations of motion are fulfilled as well. Okay, so we solved the problem of the free particle in one dimension. Now, let's see. There is one more thing that we should be careful about, because we solved the hermiticity condition and we solved the canonical commutation relations at the time t naught. Then we solved the time evolution. But how do we know that at later times the hermiticity condition and the canonical commutation relations are still fulfilled? We only checked them for the initial time. Now, in this case here, we can tell that the Hermiticity condition is fulfilled just by checking it here, right? Taking the Hermitian conjugate here for the solution x hat of t, finding that it's the same. First term is Hermitian, second term is Hermitian, so it's fine. And the same for the momentum, it doesn't even change in time. But what about the canonical commutation relations? How do we know that the canonical commutation relation is still true, still holds with our solution? Because remember, the canonical commutation relation and the hermiticity condition have to hold at all time, not just at the initial time. Now, let's check this. Check CCR. Let's check the canonical commutation relations. And for that, we just have to put this in here, x hat of t, commutator with p hat of t, is what? Well, it is the commutator of x hat of t naught plus t minus t naught. That was our solution, remember, 1 over m, and then p hat of t naught, commutator with p hat. But p hat is actually constant in time, so we can right away write down here p hat of t naught. And what is this now? Let's see. We have that x hat of t naught, commutator with p hat of t naught. So this is x hat of t naught, commutator p hat of t naught. Remember that the commutator is linear, right? And then plus commutator of x hat of t naught. It's the other term. It is this term. It's t minus t naught 1 over m p hat of t naught, commutator with p hat of t naught. Now, this is equal to IH bar times the identity matrix, plus 0. Why 0? Because this is a number which we can pull out of the commutator. And the commutator between p hat of t naught and p hat of t naught is 0, of course. Anything commutes with itself. So therefore, the commutator between x and p is IH bar 1 at all times. So that's good. But there is better news than this. It turns out it wasn't necessary to check this, because it turns out that if you found a solution for a quantum mechanical problem that obeys the canonical commutation relations at the initial moment, t naught, then it will obey the canonical commutation relations forever. That's automatically implied. The equations of motion are always of that form, and there's an elegant way to show that. Remark. If canonical commutation relations are valid for a solution at t equal t naught, then the canonical commutation relations hold at all time. That this is true for all quantum mechanical systems. So that's very useful to know. It saves us some work. And there's an elegant proof of this. Let me create more space. Okay. Proof. So, recall, if f of xp, and in fact the proof is also valid in classical mechanics, but I will write it in quantum mechanics. If f of x hat and p, or just a sec, what does it mean in classical mechanics? Well, in classical mechanics, the proof shows that the Poisson bracket is fulfilled at all time if it holds at the beginning. And here we show that the commutator, which is just a representation of the Poisson bracket, is fulfilled at all time if it holds at the beginning for your attempted solution. So let's remember that if the canonical commutation relations, if f of x hat and p hat is a polynomial in x hat and a p hat, and in principle it could of course be multiple x's and multiple p's, then the dynamics of f hat is this, of f, the time derivative of f by the Heisenberg equation, or if you write it in terms of Poisson brackets, then it's the Hamiltonian equation, is given by, well, let's write it in terms of the Hamiltonian equation. It is the Poisson bracket of f with h plus df by dt. Now, let us choose, for the purpose of our proof, let us choose that f of x hat and p hat is x hat p hat minus p hat x hat. Now, that's a polynomial in x and p. And it's a polynomial of the kind that has coefficients which is just 1 and therefore not dependent of time. So therefore we have that df by dt is equal to 0. So that term doesn't come up. So now we have then that the change in the commutator, so f dot, which is then the change in the commutator, and remember, we want to show that the commutator doesn't change, minus p hat x hat dot, right? So it's the time derivative of this, is then equal to the Poisson bracket, or we can in this case also write the commutator. So it's 1 over IH bar, because 1 over IH bar, and then it's the commutator of x hat p hat minus p hat x hat with the Hamiltonian. Sorry, I'm mixing up here the Poisson brackets and the commutators, but remember that in quantum mechanics, they're just proportional by a factor of IH bar. So we have this, right? But the important point here is that this is IH bar 1, and therefore this commutator is 0. And therefore, at any point in time, the canonical commutation relations are conserved. They don't change. So therefore, the commutator x hat p hat d by dt is 0, right? And that's true for all time, so it doesn't change. We will later see, at the moment we don't really have the tools for this, but later we will see that not only are the canonical commutation relations automatically conserved, but later we will see also the hermiticity condition are automatically conserved in time if the equations of motion are solved. So if you have a solution that solves the equations of motion and the canonical commutation relations and the hermiticity condition at the initial time, well, then the hermiticity condition and the canonical commutation relations will hold at all times. That is very useful to know. Now, we solved so far only one problem, which was the free particle in one dimension. Oh, why is it not working here? Just a sec, I need to scroll up. Okay, right. We solved the free particle. Now, another example here. Example, and that's going to be a super important example. That's the harmonic oscillator in a way that you may not have seen it before. Harmonic oscillator. By the end of this course, I will be an expert in writing in the dark. Okay, so harmonic oscillator. Hamiltonian is p hat squared over 2m plus k half x hat squared. Why is it so important? Now, cynics would say it's so important because it's one of the very few systems we can explicitly solve. True, true. But it's also intrinsically super important. And that's because it just comes up all over the place. And the reason is that every oscillator is harmonic for small enough oscillations. Let me explain. Important because every oscillator is harmonic for small enough oscillations. Why would that be true? Well, let's see. How does the harmonic potential look like? Well, if I could draw, then I would show you now a parabola. Okay, something like this. Okay, so this would be v of x, and this is x. This would be a harmonic potential. A parabola, right? So the potential term is proportional to x squared. Now, how does a real life potential look like? Real life example. Well, let's say we have a molecule such as HCl or HF or H2 or carbon monoxide, etc. These are diatomic molecules. How do they look like? Well, for carbon monoxide, for example, what we have is that there's a carbon nucleus and there's an oxygen nucleus. Both of them are surrounded by their electronic clouds, and these electronic clouds interact with each other in such a way that the carbon and the oxygen nuclei are bound together, right? So you have a molecule. Now, if the carbon and the oxygen nuclei get too close, then they repel each other because they're both heavily positive. If, on the other hand, this carbon and the oxygen nuclei get too far apart from each other, well, then they attract each other because there's so many electrons in between them, and they're negative. So there's a stable distance between the carbon and the oxygen nucleus. And in practice, these two nuclei are going to oscillate relative to each other around that equilibrium distance. And that's, to lowest order, a harmonic oscillator. Why would it be that? Let's first of all look at how this potential looks like in real life. So, the potential for a diatomic molecule typically looks something like this. So, or maybe, just a sec, that wasn't so good. It looks more like this. So this is the distance, let's call it x, between the carbon and the oxygen nucleus. And this here is the potential, V of x. We are interested in the oscillations of these molecules against each other. And why does it look like that? Well, you see, if you bring them very close to each other, the carbon and the oxygen, then they're going to repel each other, and there's very, very high energy. You need a lot of energy to bring them very close to each other because they repel each other. On the other hand, if you pull them apart, the carbon and the oxygen, well then eventually you just have pulled them apart and they become free. They're no longer bound, which means that the potential here flattens out. Right? And then that's it. Now, in which sense is this similar to a harmonic oscillator? Well, the claim is that these two potentials are very similar here. For small oscillations. And why would that be so? Let's do a Taylor expansion of our of the potential for the carbon monoxide. Taylor expansion. So what do we have? We have then that V of x, which is the actual carbon dioxide, CO, potential. This is, if we do a Taylor expansion about this point, the equilibrium point, x naught, which is the equilibrium distance between the oxygen and the carbon. So then this is, by Taylor, it's the value of the potential at the equilibrium point plus, and then we have, by Taylor expansion, the first derivative, so it's dV by dx, let's write V prime, evaluated at x naught times x minus x naught plus 1/2, this is the quadratic Taylor coefficient, second derivative at x naught. We're expanding. Remember, it's not, it's a Taylor expansion, not a Maclaurin expansion. We are Taylor expanding around, not 0, but around x naught, times x minus x naught squared. And then we have plus, and then we have 1/6 V triple prime x naught x minus x naught to the third power plus dot dot dot, higher order terms. Now, let's look at how big these things are and how important they are. First of all, this term we can forget about. It's a constant. It's just a constant energy. We know already from classical mechanics that constant energies don't matter, because if you differentiate them to get the force, 0. So it's not going to contribute. The second term is vanishing because we are at the equilibrium. And the third term is the one we're going to be interested in, because this is a harmonic potential, because it grows quadratically with the distance, right? So this is harmonic. And how about the other terms here, like this one, the 1/6 V to the V triple prime. That term is there, but for small enough oscillations, we can neglect that. I mean, roughly speaking, if the amplitude is 0.1, then, so if x minus x naught is 0.1, then 0.1 to the third power is really small. Much smaller anyway than 0.1 to the quadratic squared. Okay, so what we see here is that for small enough oscillations, if x minus x naught stays small enough, then every potential is harmonic around its minimum. That's why the harmonic oscillator occurs all over the place. And not just in quantum mechanics, but also in quantum field theory, and just all over. All right, so we want to solve the harmonic oscillator. What do we have to solve? To solve the harmonic oscillator, need to solve, as usual, three things: the hermiticity condition, the canonical commutation relations, and the equation of motion. And now let's remember the strategy that we discussed a few minutes ago. Namely, the strategy that we would try to separate the time dependence from the non-commutativity. One factor in the solution takes care of the non-commutativity, and one factor takes care of the time dependence. And hermiticity we get by taking whatever we write down and adding the Hermitian conjugate to it. Let's try that. So our ansatz is now going to be that x hat of t is some function that we still have to determine, psi of t, that will have to have a suitable time dependence times a plus psi star of t, a dagger. This is the manifestation of the strategy that we just discussed. The strategy that will take you all the way to calculating Hawking radiation, if you like. Why is this the manifestation of that strategy? Well, first of all, we have here a first term, namely this one, which embodies what we talked about. We have one factor, namely the psi of t, which is a function which is complex number valued. So it has no non-commutativity, complex number valued, and to be determined. We leave that open for the moment. Complex number valued function, and this A is our matrix from above. Remember, it was 0, 0, 0, 0, blah, 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 and then the square root of 1, square root of 2, etc., and 0 everywhere else. This is what A was. So, with this yellow box, we have a function of time that is commutative, which might be able to take care of the equation of motion, multiplied with A, which has no time dependence, but has a non-trivial matrix structure and may be able to take care of the canonical commutation relations. And then we are also writing here in this second yellow box the Hermitian conjugate of the first yellow box. And we do that just to make sure that the hermiticity condition is fulfilled. Right? So you see the strategy? We have two yellow boxes. One is the Hermitian conjugate of the other. We add them, so we're guaranteed that x hat, whatever else properties it might have, it's certainly going to be Hermitian. And the A is supposed to give us a chance of getting the canonical commutation relations right, and the psi is supposed to be such that we get the equations of motion. Now, it turns out that the equations of motion, in part, we get very easily this way. Namely, we simply define now that p hat of t Sorry, we get to that. Just a sec. Let's do it right away. So the p hat of t, because it has the equation of motion, that it is equal to, because it has the equation of motion, it is mx hat of t, we can already write down what it is. X hat dot of t. Oh, this is so tedious with this pencil here. All right, so x hat dot, right? This is one of the equations of motion. So therefore, this is equal to m psi dot of t a plus m psi dot star of t. So that's the time derivative complex conjugated of t a dagger. So this equation of motion is taken care of by making this ansatz here. Then what equation of motion is still left over? Well, remember that we have x hat dot is equal to 1 over m p hat. And so we have that x hat double dot is equal to 1 over m p hat dot, but p hat dot is equal to minus k minus k x hat, and therefore we have that x hat double dot equal to minus k over m x. None of this should be surprising because it's of course the same equations of motion as we are used to from classical mechanics. And that's because the Poisson brackets haven't changed. Okay. Oh, this is so tedious that this doesn't move. All right. Okay. So, so what we need then is this. In order to solve the equations of motion, remember that's the only thing that remains. That's almost the only thing that remains. We have already taken care of the hermiticity. Now, in order to solve the equations of motion, what we have to solve is only this equation. That's because that equation of motion we have already taken care of, right? By definition, we defined the p hat in this way such that this equation of motion is holding. Now, remember our overall strategy. We wrote an ansatz, x hat of t, as a product of a time-dependent function, which is commutative, times A, which is a matrix that's constant in time, but can lead to non-commutativity. Now, the psi has to have the suitable time dependence to fulfill the equations of motion. And how does that come about? Well, if we now plug x hat of t equal to psi of t a plus psi star of t a dagger into x hat double dot, the equation of motion, which is minus equal to k over m x hat. And then, and I leave that to you to verify, then we obtain that then we obtain that there's a condition on psi of t. And what is that condition? Well, you can verify very easily yourself. The condition is that the psi itself obeys the equations of motion, namely psi of t must obey the equations of motion. That's because the A and the A dagger have no time dependence. So the psi must carry all the time dependence, and therefore we must have that psi double dot of t equal to minus k over m x, not x, psi of t. And the solution, see, all of this is of course very easy in principle. It's just that I assume that you might not be familiar with it on the quantum level, so I'm doing it at least for once explicitly. So what we find is that the solution is of course that psi of t is equal to r, where r is some arbitrary number, omega t, plus some other constant s cosine omega t, where omega is equal to the square root of k over m, right? Because what the equation of motion says is that the second derivative has to be equal to the function up to a factor of minus times the constant, and yeah, the usual. There is something unusual here though, because all of this will work whether R and S are real or complex. In fact, it will turn out that R and S can be complex. In fact, they have to be complex. Here, R and S are generally complex numbers. Here, R and S are arbitrary complex numbers for now, up until this point. There is one more condition that we need to fulfill such that we actually solve the harmonic oscillator. What is that extra condition? Remember what we have. We have that because of our ansatz here, because of this clever ansatz here, we have the hermiticity for free. Because we just added the Hermitian conjugates to the original ansatz, so hermiticity is done. Now we've also made sure that we solve the equation of motion. We found that because A has no time dependence, we found that as long as psi solves the equation of motion, then psi times A does solve the equation of motion. And if psi solves the equation of motion, then psi star solves the equation of motion because of the linearity of the equation of motion. And then psi star times A dagger solves the equation of motion because A dagger has no time dependence. And so the sum of two solutions is also a solution to the harmonic oscillator. So the whole thing is solved if the psi is a solution to the harmonic oscillator. All right, so we have the equations of motion all wrapped up. We have the hermiticity condition fulfilled, but the canonical commutation relation still needs to be fulfilled, right? And good thing that R and S are still arbitrary. So now only need to choose R and S such that also the canonical commutation relations hold. We only need them to hold at one point in time, because then we are guaranteed that they hold at all times, because we are solving the equation of motion, and we proved earlier that this is possible. So we obtain a condition. On R and S. This is going to be homework. Not very hard. If you think about it, you just plug our ansatz into the canonical commutation relations and check what values R and S can take such that the canonical commutation relations hold. Now let me give you a little bit more explanation that will help you already also with another part of the homework. Namely, another part of the homework will concern the question of the arbitrariness in R and S. Namely, it turns out there are many choices of pairs of numbers R and S such that the ansatz, x hat of t equal to psi of ta plus psi star of ta dagger solves the canonical commutation relations, and therefore, because we have already taken care of the equations of motion and the Hermidicity, solves the whole thing. So even after imposing the canonical commutation relations, there is still a lot of choice in R and S. How to handle that choice? It's good to have choice. Can we make use of it? And it turns out we can put this choice to good use. And again, normally, I would say, oh, that's just so specific. It's just one problem. The harmonic oscillator, why do we go in so much detail? Why don't we just leave this to the homework? And I'm leaving it to the homework, of course. But why I want to tell you so much about it, and why I want to make sure that you get this exactly, is that the harmonic oscillator just comes up all over the place. And not just in approximations. Just think, for example, of the electromagnetic field. Electromagnetic waves are made out of harmonic oscillators. That's because it's wave phenomena. So harmonic oscillators are super important, therefore let's do this carefully. Okay, so let's put these choices to good use. Let's put this ability to choose R and S to good use. How? There's some very convenient choice we can make for the R and the S. So let's recall overall what we have. So we have that the Hamiltonian is that of a harmonic oscillator, 1 over 2m, and then p hat squared plus k half x hat squared. And this is the problem. And then the solution was that x hat of t is given by some psi of t, which contains the R and the S, right? A plus psi star of t, a dagger. The psi is the linear combination of sine and cosine of omega of t. And the prefactors, the constants in front of the cosine and the sine in the psi, are those numbers R and S. Yeah, and then the p hat is of course just p hat of t is just m times x hat dot of t. So we can write down the p hat of t immediately once we have the x hat of t, right? So now in here, we still have a choice. Those two numbers, r and s, let me just indicate them here, r, s, just to remind you that these functions psi do depend on r and s. Let me just show you again where it is. Where did we have it? Ah, there it is. Right, so here, psi of t is this. Right. So this psi of t with the r and the s coefficients, complex numbers in general, sits in here, in our solution. And the r and the s are partially determined in order to have the canonical commutation lessons come out right, but I'm promising you, when you check it in your homework, you find still the r and the s aren't completely determined. There is some freedom, and that we can put to good use. Namely, in the following way. What to expect for h hat now? And by that I mean, let us plug the expression for x hat and p hat into the Hamiltonian. Let's express the Hamiltonian in terms of the solution. So let us write down the solution for the Hamiltonian. Well, what we have to expect is this: h hat is equal to 1 over 2m. And then we have the p hat squared. Now p hat squared, that's m x hat dot. So this is m, and then x hat dot. So this is psi dot of t, a plus psi dot star of t, and there's an m, and there's an a dagger, and then that needs to be squared, plus k half, and then the x hat squared. Here's the x hat. We have to square that thing. So it's psi of t, a plus psi star of t, a dagger, and we square that. Now, the details don't matter. This is of the form of something a squared plus something a dagger plus something that we can work out easily, right? But no need to write this down explicitly, plus something a dagger squared, right? That's clearly what the shape of this is going to be in terms of the a's and the a daggers, because we are having here a plus a dagger squared, and here also some sort of a plus a dagger squared. So we have to expect these 4 terms. Now, that's not very convenient. We started out with a Hamiltonian that had only 2 terms, and now we have a Hamiltonian that has 4 terms. It turns out we can choose the we'll find, and this is homework, there exist choices of R and S such that the canonical commutation relations are obeyed, but also so that 2 terms vanish. Namely, this term vanishes and that term vanishes. So we can choose the R and the S such that these prefactors vanish. And that is usually done. So now you've seen the logic, the internal logic for how we solve the harmonic oscillator and why we solve it in this way, and what are the freedoms, the choices we have in here. And I'd like to make a comment, which is that what we can tell from this is that the choice of R and S will depend on the parameters of the harmonic oscillator. So notice these convenient choice. So this should be like this. This convenient choice of Rs depends on M and K of the harmonic oscillator. Okay, so this means for every harmonic oscillator, we will have a different optimal choice of R and S, such that the Hamiltonian will look as easy as it can get. All right, namely, so that it has only two terms, namely the A dagger term and the A dagger A term, and it will turn out that these two can be combined into one term, in fact. Okay, so today's lecture was clearly very methods heavy. We didn't do any we didn't make any conceptual progress here, formalism progress, but we covered how to solve quantum mechanical problems. At least a lot of quantum mechanical problems can be solved this way. Now, let me tell you again where we are and what we will do next. So obviously, in the hierarchy of abstraction of quantum mechanics, we now can go from the Hamiltonian to the conditions that need to be fulfilled, namely the differential equations of motion, the canonical commutation relations, and the hermiticity. In classical mechanics, we usually don't care about the canonical commutation relations and the hermiticity because while they are there, they're kind of trivial because everything is commutative and everything is real number valued. But in quantum mechanics, we have to spell these things out. The canonical commutation relations are not trivial, and the hermiticity is a bit more involved than just realness. Anyway, so what we can do is we can go from the Hamiltonian to the equations of motion, and what we have discussed in the previous lecture and also today is methods for actually finding solutions x hat of t and p hat of t, and if there are multiples of those, then the x hat I of t and p hat I of t. And they obey the canonical commutation relations in particular, which means these are not number valued functions of time. These are solutions, all right, but not number valued solutions. So what we still have to do is find out how we can boil these things down to number predictions. And this is what we will pick up on in the next lecture. Okay, so I see you then.